Let me talk about shear locking. When shear locking occurs, the shear locking is the problem with full integration of first order hex or quadrilateral elements. Let's see it with simple example. So when this is a particular structure or single element, you can imagine it is subjected to pure bending moment M, and this is a expected behavior as we know. However, CPS4, that is a 2D quadrilateral element or hex element C3D8, it behaves in a manner as shown in the figure. This is because there is a linear interpolation of displacement across the edge of element, and since it doesn't have a mid-side node, it cannot capture the bending in a curved manner. Now let's zoom into the element, finite element, CPS4 element. Okay, let's try to understand with 2D element. The same analogy applies to 3D hex element. This is the quadrilateral element first order, and it has four integration points. As we know, the element integration points are internal to the element. Now this is a subjected to bending moment, and this is the deformed behavior of this element. As we can see that this top edge gets shortened, and the bottom edge becomes wide. Okay? So this is how the bending behavior is, and because of that the no integration points 1 and 2, if we see, they move apart. Okay? So this integration point 2, earlier it was here before deformation, it moves this way, and integration point moves the left side. Similarly, integration point 4 moves in, and integration point 3 moves inside like this. So because of that, this particular edge, we can say it is shortened. Now, visually, now let's try to understand shear locking. We will understand in both ways, one visually and with mathematical and hand calculation. Let's talk about visualization. So here we can see the angle between these two lines which were perpendicular before deformation. The angle is changing. Okay, so we know the shear strains means angle change in angle, and integration point 1 and 4, as we can see, there is a decrease in angle. Okay, it is less than 90 degree. So this integration points they exhibit no, positive shear strains, whereas integration point 2 and 3, which were 90 degree earlier, there is a increase in angle. So these two integration points, there are negative shear strains. Okay? So this is IP2 integration point 2 and integration point 3. The positive shear strains are developed at integration point 1 and integration point 4. So we can say that this element, first order quadrilateral or hex element, full integration elements, under pure bending, they generate shear strains and shear stresses, which should not be the case, because the pure bending characteristics are that it doesn't produce any shear stresses. So the summary of previous slide is that first order hex or quadrilateral elements, full integration elements, they generate parasitic shear stresses, that is undesirable shear stresses in pure bending. And this generate, because there are shear stresses, it also generates internal shear forces, as we know. So this produces a internal resistance, and the elements behave in a stiffer manner. That means we can say the element gets locked in shear, or in other words, it behaves stiff. Let's try to understand this, how it behaves stiffer. For example, there is a beam here. It is subjected to bending moment. If based on stiffness of the beam and geometry of this beam, if under this bending moment, okay, if it is supposed to have peak deformation at this end, for example x mm, okay, since if it is a CPS 8 element, it behaves stiffer. That means the actual deformation in FE analysis is less than x mm. Okay. Let's try to understand this in a reverse order. Uh, for example, instead of moment, let's apply rotation theta. Okay. Now this rotation, as we know, it produces displacements. So after doing FEA analysis, we get primary solution variable, that is a displacement of this beam. As we know from displacement, we get strains. And earlier we have seen in the slide that the displacement, when there is a displacement, it generates shear strains and bending strains. So these strains include bending, which are axial bending plus shear strains. So this is pure pure bending problem, which is supposed to have only bending, but we are getting undesirable shear strains as well because of the formulation of this element. Now this bending shear strains produces or we can compute bending stresses from bending strains, and we can also compute shear stresses. And this bending stresses generates internal forces. So we get internal forces plus due to bending. So this is basically a resistance, internal resistance, and we also get internal forces due to these shear stresses. So internal forces, which is a resistance to the external force or boundary condition, that is contributed from both bending and shear stresses. So if we see here the rotation theta, which is supposed to generate only internal forces due to bending, also generates internal forces due to shear stresses. Okay, so we get additional or parasitic internal shear forces. And as we know, the total force or reaction force here, what we get, that is total internal force due to bending, okay, this one plus this. Okay, so at all the nodes, okay, if we take all the solid elements or multiple more than one element. So now we can see here the reaction force which was supposed to come only from bending is also contributed by shear forces, and that's why we can say that no, in pure bending, CPS 8 or first order hex or quadrilateral element, they behaves stiffer, okay, because we get additional reaction forces due to shear. So this reaction force is more than theoretical or actual value. So now we have understood tier locking by visualization and also practically. Now let's see shear locking in mathematical terms, okay, or with hand calculations. So as we know, the if we'll take simplest shape of the element CPS 8, minus 1, minus 1, 1, minus 1, 1, 1, and minus 1, 1 global coordinates. Okay. We have seen this in module 3. Please revisit module 3 if you want to understand this concept well. So this global coordinates, we know we can map into natural coordinates using a Jacobian. So since this element is perfect square shape and also situated at 0, 0, when we put local or natural coordinate system here, zeta and eta on this element, and then map, we get obviously the same coordinates of the nodes 1, 2, 3, 4. Since we want to understand the concept, we are taking a simplest or perfect shape and with the 0, 0 as a center of the element. So these are my natural coordinates zeta, eta. Okay. And these are the blue color are nodes, and the black internal numbers are integration points. Okay. And since the location of this 1, 2, 3, 4 are just shown approximately, they may not be the actually as per the scale, but the coordinates in terms of zeta eta of these integration points are as per Gauss quadrature rule. They are plus or minus 1 by root 3, and y coordinate is plus or minus 1 by root 3. So with this, let's try to understand. Okay, and we have seen this in module 3, the shear strain vector epsilon. Okay, it is related to displacement vector by B matrix. So B is also called strain displacement relationship vector, and they consist of derivatives of shape functions. So for first order quadrilateral element, this is the B matrix, which is epsilon U relationship. Now let's write this strain vector for natural coordinates. Okay, since it is same mapping, okay, same coordinates are being mapped. The coordinates are being mapped to the same location as global coordinates. This uh, matrix will remain same, except y will be replaced by eta and x will be replaced by zeta. So let's rewrite this, and this is my strain displacement matrix B in natural coordinate system. Okay. After B is after transformation. Okay. And this is the reason we have taken simplest element shape, so that we need not to do B transformation. If for example, if we take in global coordinate system, if element is somewhere like this, and we do a local natural coordinate mapping zeta eta, for this element, the B matrix is not going to be same. Okay, it is 3 by 8. Okay, but the terms will be different. However, the nature of B matrix will remain same. Okay, it is not going to change the shear stresses or strains on bending stresses and strains. Okay, so let's come to this. This is strain vector. As we know, epsilon 11 and epsilon 22 are bending strains. Okay, in direction 1 and direction 2. They are also called axial strains. Sorry, normal strains. So we can multiply the first row with this displacement vector and we get epsilon 11. Similarly, epsilon 22, we can multiply this second row with this displacement vector column and we get epsilon 22. Similarly, epsilon 13. So we will not see epsilon 11 and epsilon 22 in shear locking. Okay, we'll focus on epsilon 12. We will see this in next upcoming chapters in R glass. So let's see this epsilon 12 shear strain. Okay. So epsilon 12 I have written it here again. Now let's try to understand shear locking with no, hand calculation. What we will do, we will take the displacement values. For example, the deformation has occurred and we got the displacements at node 1, 2, 3, 4. Right? So as we know, uh, this is the deformation, right? In pure bending. So let's assume some values of displacements u1, u2, u3, u4. These are the displacements at node 1, 2, 3, 4 respectively. And the internal numbers 1, 2, 3, 4 are integration points. So as we know, stresses and strains are calculated at integration points and our shear strain is given by this formula. Okay? And if I put all the values u1, u2, u3 in u4 and v1, v2, v3, v4 which are 0, as we know the y displacement is 0 here, v is 0. So we'll put all substitute all u and v values here and we get epsilon 12 as minus zero point 0.1 zeta. Okay. So the shear strain is a function of zeta. That means it is not constant. It varies with within element. Okay. And the most important thing is that as we have mentioned earlier, uh, pure bending characteristic is that epsilon 12 is 0. Okay, that is pure bending. But here in this case, in this pure bending problem, okay, we are getting epsilon 12 as minus zero point 0.1 zeta, which is not equal to 0. So we get some shear strains which are called parasitic or undesirable shear strains. Okay, now we know the natural coordinates zeta eta values, okay, for all these integration points. Okay, in previous slide we have seen this. We have this zeta and eta values. So these are the coordinates of integration point 1, 2, 3, 4. If we substitute these zeta values for all integration points, okay, all four integration points, okay, here in this, then we get shear strains. Okay, for example, for ip4 we substitute zeta is equal to minus 1 by root 3. Okay, similarly for ip1 as well, and for ip2 and 3 we can substitute zeta is equal to 1 by root 3. By substituting these values here in shear strain formula, we get shear strains at ip4 and ip1 as 0.058 and yeah, 0.058, whereas ip2 and 3 integration point 2 and 3 we get negative value of shear strains. Okay. And this we have seen visually earlier. We are just proving it with the hand calculation. So let's go back to that visualization here. Okay. We have talked that the increasing angle, okay, which is IP2 and 3, okay, that is generating that means negative shear strains. Whereas IP1 and 4, there is a decrease in angle, it is positive shear strains. So here that's what exactly we get here. Hope the concept of shear locking with a simple hand calculation and example, it is pretty much clear. The summary is that in pure bending we should not get any shear stresses, but due to the formulation of full integration first order hex or quadrilateral element, uh, they generate parasitic shear stresses and strains under pure bending. That is called shear locking. So in next chapter, we will see the workshop on shear locking. We will see how we see, how we get additional or undesirable shear stresses with hands-on demo, and we will also discuss about how to solve this problem.